All right, in section 12.2, eighth graders, we're talking about independent and dependent events. You can read over this yourself, but you should already know from sixth grade, an independent event is when one event does not affect the other, and a dependent event is one event does affect the other. I'm more concerned in this unit or this section about your terminology and how you write the probabilities. So here it is, and this is how we write it. The probability of independent events. Two events, A and B, are independent events if and only if, it's a biconditional, if the probability that both events occur is the product of the probabilities of the event. So here's how we write it. The probability of A and B happening. You're going to find the probability of A, the probability of event B, and you multiply them together. Let's say you roll, you want to see the probability of rolling a 1 and the probability of flipping a coin. So the probability of rolling a 1, we'll call that probability of event A, is 1/6. The probability of flipping, let's say heads, is 1/2. The probability of both happening would be 1/12. All right, example 1. A student taking a quiz randomly guesses the answers to 4 true-false questions. Use sample space to determine whether guessing question 1 correctly and guessing 2 questions correctly are independent events. Now, by looking at it, I'm hoping you see that these are independent. What you guess on the first question will not affect what you get on the second question. So let's just figure out the probability. Question 1, you could get true. Question 2, you could get true. You could get true, false, false, true, or you could get them both wrong. So, what's the probability here of guessing both of them correctly? It's 1/4. Easy peasy. But now this is the important part. This is what I want you to do. If it's independent, if you follow the rules of independency, it should be able to work out and give you the exact same value. We should end up with 1/4. So, here's what we're going to do. What is the probability that you're going to answer the first one correctly? Well, it's 1/2. What's the probability you're going to answer the second one correctly? It's also 1/2. If it's independent, we should be able to multiply both of them together and get what we got here. And because 1/2 multiplied by 1/2 does indeed equal 1/4, we know that these are independent. And voila, we've just mathematically proven that this event is independent. So question 2, we have to determine whether selecting a girl first and randomly selecting a second girl are independent. Again, you're going to look at this and go, okay, if a group of 4 students includes 1 boy and 3 girls, and the teacher randomly selects one of the students to be the speaker and the different student to be the recorder, and then you have to determine if it's independent, you're probably thinking, well, if one student is chosen, it's going to depend on the first person who the second person is. So you know they're going to be dependent. And here's how you check it. I'm not concerned with you just looking at a problem and telling me it's dependent or independent. What I'm concerned with is that you're able to prove it mathematically. So here we go. So here are all of our outcomes. We could have girl 1 picked and then a boy, girl 2 and a boy, girl 3 and a boy, girl 1 then girl 2, and so on. So you can see all the different combinations of those 4 students. So what is the probability that a girl is going to be picked first and second? Well, a girl being picked first and second are all of those. So that is going to be 6 out of 12, which is equal to 1/2. So we know it's 1/2. Here's how you determine if it's independent or dependent. If it's independent, we could find the probability of both things happening separately, multiply them together, and it should give us the same thing. So what is the probability that we have a girl first? So let's think about this. We have four people. How many are girls? 3. So what's the probability that a girl is going to be picked first? 3/4. Now we're looking at this individually. What is the probability of a girl being picked second? Now again, we're just saying separately, completely separately. We have 4 girls, 4 people, 3 are girls, so it's going to be 3/4. So the probability of both happening, 3/4 multiplied by 3/4 equals 9/16. Since 9/16 does not equal 1/2, the probability is dependent, which means it's not independent because they are not equal. So because they are not equal, that means that they are not independent. They are dependent. All right. So this first paragraph, if you want to read over it, explains what we just talked about with independent and dependent events. But here's the next thing we're talking about, is conditional probability. Now, a probability, or the probability that event B occurs given that event A has already occurred is called conditional probability of B given A. So this is what it looks like. The probability of B given that A has already happened. So again, the probability of B once A has already happened. The probability of B, event B happening once A has occurred. Okay? That's conditional probability. It's dependent. We depend on what happened in A before B actually happens. So, here is our concept. If 2 events, A and B, are dependent events, then the probability of both events occur is the product of the first event, which is the probability of just A, multiplied by the conditional probability, which is the probability of B given that the first event has already happened. So, how we would write it here, the probability of the girl first and the girl second would be the probability of the girl first. And remember, the girl first, we have 3 girls, 1 boy. So the probability of the girl first would be 3/4 multiplied by, now the probability of picking another girl, the girl second, if the first girl has already been picked. So what's the probability, if the first one was a girl, that the next one's going to be a girl? Well, we now have 2 out of 3 girls. We multiply that, and that's going to give us a probability of 1/2. Again, I'm more concerned about you understanding this right here. Right there. So example 3. As part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. Again, what I am concerned about is how to write this. I know you know what to do. So we have to do the probability that you get a 5 on your first spin. So that's going to be the probability of 5, which is 1/8. The probability that you get a number greater than 3 would be 5/8. So the probability of getting a 5 and a number greater than 3 is going to be 1/8 multiplied by 5/8, which is 5/64, which we need to write as about 0.078, which is about 8% or 7.8%. So any one of these would be correct. This is probably what you're going to see most of, is either a fraction or the percent. Example 4. A bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag and set it aside. We know it's going to be dependent because one depends on the other. Then you randomly draw another bill from the bag. Find the probability that both events, A and B, will occur. So we have to write it down correctly. So the event A, first bill is 100. And then event B, the second bill is 100. So we start with the probability of A. What is the probability that the first bill is going to be 100? Well, we know that there are 25 bills total, and 5 of them are 100. So it's going to be 5/25. The probability of event B, now, see what I just did there? That's incorrect. Because the probability of event B would be that we're just pulling out a $100 bill. We have to have B given that A happens first. This is the conditional probability. We have to write that the probability of B given that A happens first. So, if A happens, then what's the probability that the next bill is going to be 100? It's going to be 4/24. So now to do both together, it's going to be, whoa, let's fix this. Sorry. It's going to be the probability of event A multiplied by the probability of B given that A has happened. So we're just going to multiply them together. 5/25 multiplied by 4/24. That would give us 1/5 multiplied by 1/6. It is approximately 0.033 or about 3.3%. As an exact fraction, it would be 1/30. Any one of those would be acceptable. Now, example 5, comparing them. You randomly select 3 cards from the standard deck of 52 playing cards. What is the probability that all 3 cards are hearts when you replace each card before selecting the next card, or do not replace it? So try this on your own. See if you can set it up. Do both of these, part A and part B. Pause the video and you can do this on your own. And do it with correct notation. So, something you may not have noticed is that we have 3 things happening here. So the probability that all of them happen, in A, if you replace them, you can actually do this with 3 terms. So since these are all independent, you're just going to take the probability of first event multiplied by the probability of the second event multiplied by the probability of the third event. So the probability that the first card is hearts, well, there are 13 hearts out of 52, multiplied by 13 out of 52, multiplied by 13 out of 52. That gives us 1/64, which is approximately 1.6%. Now the next one, the same process, the probability of A and B and C. But it's going to be the probability of A happening multiplied by the probability of B given that A happens, multiplied by the probability of event C given that A and B happen. So the probability of A, 13 out of 52. What's the probability of B given A? We pulled a heart out. The next one needs to be a heart. There's 12 left out of 51, multiplied by 11 out of 50. That would give us 11/850ths, or about 1.3%. Next example. A quality control inspector checks for defective parts. The table shows the results of the inspector's work. Find the probability that a defective part passes, and then the probability that a non-defective part fails. So in part A, we are just finding the conditional probability. We want the probability. All right, so here's how we do it. Since, right here, we have to know the probability that a defective part passes. So what has to happen first is the part has to become defective. So of those that are defective, that's event A, how many have passed? So given part A, what's the probability that event B given part A? So the probability of a defective part passing. So the first thing that has to happen is how many are defective? Well, there are 39 total ones that are defective. Then we have to figure out how many of those pass. Well, that's going to be 3, which you know is 1/13, which is approximately 7.7%. Now we have to know the probability of a part failing after it's already been labeled non-defective. So how many are non-defective? 461, not 6. Good thing I can add. Of those that are non-defective, how many failed? 11. So that's going to be approximately 2.4%. So here's the next piece, is you can take the formula for the probability of dependent events to write a rule for finding the conditional probabilities. So take this right here. The probability of A and B is equal to the probability of A happening multiplied by the probability of B given A. If you want to find this, you treat it like a variable. So if I just divide both sides by P, the probability of event A, you get this right there. And you can set up your own formula. Last problem. At a school, 60% of students buy a school lunch. Only 10% of students buy a lunch and dessert. What is the probability that a student who buys lunch also buys dessert? Well, the first thing we look at is right here. We want to know the probability that a student who buys lunch also buys dessert. That right there is the conditional probability because one has to happen before the other. So we know this is dependent events. So we have to determine which one's probability A, or like event A or event B. Since, let's see here, what is the probability? A student who buys a lunch also buys a dessert. So those who buy lunch then buys a dessert. So this has to happen first. Buys lunch. So A, probability of A, I'm going to put an A here, is buying lunch. And B is buying dessert. So here we go. What's the probability of this? 60% buy a lunch. Well, 60% buy a lunch. A is that. So that means this is 60%. We're writing it as a decimal. Multiplied by the probability of both happening. Well, that's X. We don't know it. Then the probability of A and B, it says right here, 10% of students who buy lunch also buy dessert. So that means the probability is 10%. So now we just have our equation, 10% equals 60% X. We divide both sides by 0.6. X equals 1/6, or about 16.7% is the probability that a student who buys lunch also buys dessert.